Welcome, we are Group 22016, the Real-Time Instrumentation Characterization Kit version 4.0, or for short, RIC v 4.0, sponsored by Roche Tissue Diagnostics. We are tasked with creating a system or tool that can measure the volume of liquid dispensed onto a microscope slide. This slide will be placed within the Ventana Benchmark Ultra, which is an automated tissue staining instrument that has dirty individual slide drawers that allows the user to stain multiple slides. The Benchmark Ultra and other automated tissue staining instruments could be used to diagnose diseases. The automated staining process is performed on a microscope slide that contains a tissue sample and by running it in controlled internal conditions. The volume dispensed on the slide could undergo a change in volume from the conditions such as humidity or temperature in the Benchmark Ultra. By measuring the fluid on the microscope slide in real time, one could better understand the staining environment and carefully monitor the staining process. This is where the project is mainly centered, since this is where we have to incorporate our design.
Hello, my name is Josh. I'm the systems engineer. Here we see our prototype, and we're going to go ahead and explain the technology that powers it. Our system consists of two main parts. First, the red box, and second, the load sensor, all provided by FuTech. The red box is an amplifier and a collector all in one combo. It collects all the data, sensor data from the load cell, and then it outputs it to its own software, as well as amplifies the power so that readings can be a little bit more clearer. The second half of our system, the load cell sensor, allows us to approximate the volume of liquid on top of our stained slide. The way this works is through a Wheatstone bridge. A Wheatstone bridge essentially consists of 4 resistors. 2 are in series, but in parallel with the other 2. And between these 2 parallel sets, a voltage difference is measured. If everything is balanced within the circuit, that voltage difference will be 0. However, if a weight is applied, such as a volume of liquid, then R sub x will change, yielding a different voltage difference. That resulting voltage difference will then be captured to the red box and sent over to the soft. We will approximate the volume of liquid being applied on top of the load cell sensor. We have our 5 main system requirements: resolution, accuracy, precision, volume range, and settling time. Resolution and volume range were provided to us by our sponsor in their statement of work. Accuracy is to ensure that our data collected from our sensor is in line with our project scope. Precision is to ensure that every data point we capture does not have any large deviation, which in turn will build confidence with the measurements collected. Lastly, the settling time we created to be about 30 seconds. However, during our testing, we found out that that might be too small, considering some tests can run up to 16 hours within the Benchmark Ultra.
Hi, my name is Mark, and I'm the procurement lead on the team. And I'm going to be going over our FAT test procedures, starting with our resolution test, where we set up the RIC4 with components, launch the FuTech software, place the slide on the RIC4, tear out the scale to ignore the weight on the slide, and then for each of 9 different tests, with the preloaded slide, we would place a weight on a scale and run 30-second long tests with 5 samples per second. We'd set a file path and run the test. Halfway through, we would add an additional 10 milligram weight. 10 milligram weight being the analog of 10 microliters of additional liquid, since we're trying to estimate resolution to that range, was added midway through. And then we would just look at the endpoints, take the differential measure, and see if it's within 10 microliters. This was per our sponsor's request. Once all those tests were done, then we would move on to accuracy and volume range. This is essentially the same test but looked at from two different lenses. This test was also done with hour-long tests, but at 2 samples per second, and with the same general setup procedures, with weights that sort of in a logarithmic scale, so 10, 20, 50, 100, 200, 500 milligrams, and 1, 2, and 4 grams. The reason why we're not doing 5 is so we don't overload the weight scale given the 5-gram slide that we're preloading it with, and it has a 10-gram max capacity. After these tests are completed, then we would check to see the percentage. One would check 1 minus estimated over actual and make sure it's greater than 90%, and the other test would be just estimated over actual to make sure it's less than 10%. So it's essentially the same test, but just looked at two different lenses, one representing accuracy, one representing volume range. And then this test, which is the precision test, uses the test results from 1.6, uses the same test procedures from 1.6.2, but those results, and then calculating standard deviations and means for each test. And this was calculated as a percentage of standard deviation over mean, and we wanted to make sure that's within a tolerance of plus or minus 5%.
Here is our verification table, and as you can see, most of our requirements did pass, barring one, settling time. Settling time did fail, but that was mostly because of the way that the requirement was written. And on the right side, the resolution passed without any uncertainty, and accuracy, precision, and volume range passed, but with exception. This was because when conducting our final tests, 7 out of the 10 tests did pass, and only 2 failed. With these results, our team felt uncomfortable marking the whole test as failed since majority did pass, therefore we went with pass with exception.